So we are going to speak about again electric potential. It's always electric potential because that is a chapter, but this time we are going to speak about a uniformly charged thin spherical shell. That's a new idea we are going to discuss. Now, how do we do that? Now, let's firstly assume. Firstly, let's imagine a thin spherical shell like this. Okay, it's not a spherical shell yet. I'm going to make it. Okay, so now this becomes a thin spherical shell. Now, what could be a thin spherical shell? Now, if you imagine a plastic ball which is hollow inside, and the surface, the ball itself is very thin. It's an example for a thin spherical shell. Now, the center of the spherical shell is here. Now, there is a radius. We are looking at only the internal radius, that is r. The external radius also would not matter because the spherical shell's thickness is very less. So r would be the considered external radius also. That confusion should not arise. I'm taking a point P, and as of now this point P lies outside the shell. Now I'm drawing a line from this point. Oops. This is the line. Now this distance is r. Now firstly we should know that when we speak about the electric field, the electric field acts as if it is concentrated at the center. At the center of the sphere. So as a result of that, because it is there is the charge on this sphere, and it acts as if it is concentrated at the center. So that kind of means it acts like a point charge. If that is the case, I could find the electric potential at the point V due to this point charge, which is given by a formula 1 by 4 pi epsilon naught Q by R, which is R is the distance of the point. Right? Now, instead of having the point outside the shell, what if the point P lies on the shell? If we do that, then R will become capital R. So P becomes here. So R becomes capital R. So V equals 1 by 4 pi epsilon naught to Q by capital R. Now what happens if P lies inside the shell? Inside the shell, if you look at electric field, it is zero at all points inside the shell. As a result of that, the electric potential constant at all points inside the shell. So we could then go for the formula V equals 1 by 4 pi epsilon naught into Q by R. That is constant inside the shell. Now we have looked at 3 different scenarios. P was first outside the spherical shell. Then I moved P to the surface of the spherical shell. Then P came to the center of the spherical shell. Now can we visualize how the potential is varying as a result of that? Now let's do that. Okay, so this is the spherical shell, this is the center. Now I'm going to see how the variation of the distance looks like as R increases. I'm taking that on x-axis. Oops. I will take the potential on z-axis. Now, when we are inside and till it reaches outside, if you look at the formula for all the points inside, this is what we got, and for the points on the shell, this is what we got. That means from if the point is anywhere inside the shell up to even the surface of the shell, it is a constant electric potential. Now that constant electric potential, so till this point it is constant, which is given by the formula 1 by 4 by epsilon naught into Q by R. What happens after that? After that, it switches to 1 by 4 by epsilon naught Q by small r, right? And then as the R keeps increasing, so as R increases, the potential decreases. So that is going to look like this. So this is inside. Then as R increases, the potential is going to keep decreasing.